Hello, Calculus AB. Mrs. Jurosik here again. We are now going to go through Fundamental Theorem Part 1. Hopefully you've done plenty of practice with Part 2. Part 1, should be a much quicker video, and we're going to kind of get to see the pattern within the first 3 examples of what's actually happening. This is considered something that should make life a lot easier to calculate when you're presented with this situation. So we show the first few examples using a full method, if you will, with many steps involved, but then you'll start to see some pattern emerge where the goal is to get you to the place where once you see a problem like this, you can go directly to the shortcut, if you will. Okay. All right, here we go. If you haven't printed out your notes, please go ahead and do that or get your notebooks ready. But let's just start. So first thing to notice that's different from what we were doing in Part 2, Fundamental Theorem Part 2, is we do definitely have a different notation within our problem. We have this ddx right in front of our integral symbol. So that means we are taking the derivative of an antiderivative. So some of you may automatically be thinking, well, don't they undo each other? Yeah, they basically do. So bear with me. Let's do a few problems and let's just see what's going to actually happen. So we are going to take this through what I would like to call a, I guess, longer method, or the official, like, we're going to do this problem the way it's written. We're going to find the derivative of this integral of 2t from 5 to x. Okay. All right. We start with the part that is the integral. So when we take the antiderivative of 2t, now notice we do have bounds, so we're not going to add a plus c, but we have to take the derivative. The derivative of 2t would be t squared. Hopefully everybody agrees. We're evaluating it from 5 to x. And in the end, once we're done doing that, we are going to take that derivative. So I'm going to finish the antiderivative portion of this, or the integral portion of this, okay? So that means if I'm evaluating, I plug in my upper bound first, and then I subtract after I've plugged in my lower bound. So that would mean that I have x squared minus 5 squared. So to denote them being plugged in, if you will, just to make it. Okay. Well, if I evaluate that, it's just x squared minus 25. And then I would need to take the derivative of that expression. Well, what's the derivative of x squared minus 25? It is 2x. Okay. Whether or not you're seeing what's going to happen from just one example, I don't know, but I'm going to move right to the next example and go ahead and start that one. So again, we're taking the derivative of the integral of 2t squared plus 3 from 5 to x. So first of all, I need to take the antiderivative. So I add 1 to the exponent, so that's t cubed, and I have to divide by 3. So 2/3 t cubed plus 3t evaluated from 5 to x. So I'm plugging in my upper bound, 2/3 x cubed plus 3 times x minus 2/3 times 5 cubed plus 3 times 5. And all of that I have to take the derivative of. Wow. Seems like a lot of stuff, huh? 2/3 x cubed plus 3x. That's not too bad. Minus, now I'm pausing for a second because all of this is some large number, right? So we're going to get a number here. Why am I doing that? It's a constant. And if I'm going to go ahead and take the derivative of this anyway, what would happen to that constant? It's 0. So when I go to take the derivative of 2/3 x cubed plus 3x minus some number, I end up with 2x squared plus 3. You might already be catching on to this. Okay. One last one for good measure. We're going to come back to a longer method again before the notes are done, but let's do one more just to make sure we maybe are seeing what we need to be seeing. All right, antiderivative integral of 3t squared plus 4t minus 2 is t cubed. I'm going to put next down already. Can't help but jump there, right? T cubed plus 2t squared minus 2t evaluated from 3 to x. X cubed plus 2 times x squared minus 2 times x minus. Now all of that, right? 3 cubed plus 2 times 3 squared minus 2 times 3. That's a lot of stuff. And then after that, we're taking the derivative of all of it. Do I have enough, maybe one big bracket around all of it? X cubed plus 2x squared minus 2x minus, and again, what do we have? One big constant or number, right? Derivative of x cubed is 3x squared. Derivative of 2x squared is 4x. Derivative of negative 2x is negative 2. Derivative of a constant is 0. So I hope that something that is happening that you are seeing is that we are replacing our whatever the dummy variable is in the problem. In this case, they were all t's. I would say t is a very popular dummy variable, are simply replaced with x's. As long as, if you notice, right, your lower bound is the constant. So what's also a theme here? Lower bound is the constant. And the upper bound is the variable. Now, hang on to that real quick, because I'm going to add, actually, that's why I'm putting an asterisk by variable, because we're going to see something happen in another few problems. But looks like we rewrite the function itself exactly the same way and just put an x in it. Okay, well, if that's the case, for problem 4, instead of doing all of this or going to the calculator, because remember, we don't take the antiderivative of natural log. We discussed that with part 2. So if instead I am just going by the pattern I've seen, I literally rewrite what I have with the x plugged in. That was my answer. All right. That is Fundamental Theorem Part 1. At least that's part of it, okay? It is that easy, but it can't all be that easy. So there's a couple more types of nuances we're going to put to this so that you know how to do all the types that could be presented, okay? So you'll notice you still see your telltale sign that you have Fundamental Theorem Part 1 is having the d dx in the front, right? All of them had the d dx in front. That is your clue. D dx in front of an integral symbol, Fundamental Theorem Part 1, Fundamental Theorem Part 1. Fundamental Theorem Part 2 will not have the derivative notation in front, okay? And it will have 2 bounds, a lower and an upper bound. Also something to note right now, notice how your upper bound is now not just an x. All of these were x's, right? Now we have a cosine x. That adds a little bit to our process. For the most part, our process is the same. But what I'm going to do with this one as an example is I'm still going to go through it the longer way so you can see how it works with having the cosine x, okay? So same rules, meaning I take the antiderivative portion first. So your antiderivative of 2t is again, t squared. And I'm going to evaluate that from 5 to cosine x. And I didn't need to be so liberal with my parentheses. Okay. So I'm going to go ahead and plug in. Okay. Which gives me cosine squared x, if you will, minus 25. And I'm going to take this derivative. So did I really need to do the cosine squared x notation? No, because now I need to take the derivative. So I actually would like to look at it in this manner when I'm taking the derivative, right? Power rule applies. So I'm actually doing 2 cosine x, right, to the first power. And then what do I have to do? Chain rule, everybody, chain rule. So the 2 comes down in front. I take 1 away from the exponent, but then I have to take the derivative of the inside, which is negative sine x. And then the derivative of 25 is 0. It's a constant. All right, so let's look at what we have. So I have as a final answer, maybe to make it a little bit neater looking, I'll take the negative out front. Negative 2 cosine x sine x. Okay. So let's think about our pattern from before real quick. We were just before taking the t out, if you will, the dummy variable, and plugging in the x, which was always located here. Okay. Do you see anywhere in my final answer just 2 and cosine x? Sure. Right here. Okay. If you even look at the step before, there's my 2 cosine x. Well, before, when our upper bound was always just x, which what is its derivative? What is x's derivative? It is times 1, right? So that is chain rule. But when it's times 1, we don't think about it. Well, here we have to think about it. Our upper bound is no longer just x. It's cosine x. We have to take its derivative. So what is the derivative of cosine x? It is negative sine x, which in my final answer was there. So what is the moral of the story here? If your bounds at all are functions other than 1x, the derivative of the bound needs to be taken. The derivative of the bound needs to be taken. Okay. All right. So let's go to the next example. I am actually going to go ahead and do this one as well the long way, just to be sure we're following along. So antiderivative of 2t squared would be 2/3 t cubed plus 3t. We're going from 5 to sine x. All right, so 2/3 sine x cubed plus 3 times sine x minus 2/3 5 cubed plus 3 times 5. Again, it's just that constant. And I think I needed that one and a d dx. Okay. So again, just a constant. So when I go to take the derivative, it's going to zero out. All right. When I go to take the derivative right here, I'm not going to rewrite it. I'm actually going to leave the 3 exactly where it is because power rule comes first. So 3 times 2/3 gives me 2 sine x, right, to the second power. But then I have to take the derivative of sine, which is cosine, plus 3 cosine x. Okay, so take a look at what I have. And then remember, this would be minus 0. I have nothing that's a constant, so the derivative is a constant. All right, So it doesn't look exactly the same as what I had, but we can do a little bit of work with it. If you would like, we could take out a cosine. We could do a couple of things with it. Okay. So we could take out, let's see, we could do cosine x, giving us 2 sine squared x, right? Plus 3. Looks a little bit better, doesn't it? I've got 2 t squared, which then we plugged in the sine x in place, which would give us sine squared x plus 3. Have to take the derivative of your upper bound, which happens to be sine, so there's my cosine. If I went straight to just using what I had in the previous problem and what we had gone over, when you think about doing this, you always take, as long as your lower bound, right, you've got your constant, you know that's going to zero out. I'm going to take my upper bound, plug it directly in. Right? And then my final move, right, that's the plugging in of the upper bound. My final move is to have to multiply by the derivative of the bound. And that is exactly that. Okay. I have this one last problem in here as well. Let's go directly to our, what we're supposed to do, our pattern. Okay. So we're supposed to just plug in the upper bound. Uh-oh. The upper bound is now the constant. That is the order of integration property at work there. The unknown or the function needs to be the upper bound if the other bound is a constant. So long story short, constants should be lower bound. Okay, so we need to rewrite the order of this. Okay, there's my negative sign. And what I would be doing is simply plugging in that. And that is your final answer. Done. All right. I'm going to add a few problems right now. We're going to do a couple of more ideas here. What if that was our, let's call this 8. Look at that. So now we have a completely different situation. There is no constant as a bound at all. 2 different functions. Order doesn't matter then. As long as both of your bounds are functions, they can be in any order they want to be. Your rules would now be, you literally just keep the sine of t as the sine, and you plug in your upper bound. You have to take its derivative. Then you're going to subtract, plugging in the lower bound function, and then take its derivative. Okay. If you've been following everything that's been going on, it makes sense as to what you would do. We've just added another function into the mix of bounds. Okay. So again, we're staying with sine of ln x, plugging in the upper bound first, but then we have to take the derivative of ln x, which is 1 over x. Then we're subtracting the sine and plug in the lower bound. And then we have to take the derivative of the lower bound. And we are done. And we would leave this as our answer. We are done. So again, when our situation is that we have 2 functions, we take the upper bound and we just plug right in, which we did, and then take its derivative. Then we're doing our subtraction. So this reminds us of fundamental theorem part 2, right? We're evaluating at both of our bounds. However, our bounds are functions. Okay. And then we take the lower bound, we plug in, and then we take the lower bound's derivative. Final answer. Let's put up one more of those. Okay, we'll do one more. How about tan x and 4 e to the t squared dt? I'm actually going to put up, I think I've got, do I have any more I want to do? I will do another two functions. So while I'm writing out another one, why don't you try and do 9? Since I made that one the upper one, let's switch that around. Okay, let's pause and come back. Okay, so go ahead and check your work. A couple of just things I want to comment on. This was out of order. The constant was in the upper bound position, so I do have to use the order of integration property, which I did right there. And then I went ahead and plugged in my tangent into the place of t, right? Tangent x goes in for place of t. And then you have to take the derivative of tan, which is secant squared. So I have my negative sign because of the order of integration. This is my replacement of tangent into t, and then my derivative of tangent. And then for the last one that I had done, the derivative or ddx of integral from ln x to cosine x of t squared minus 5t dt. All right, so two functions, order does not matter. So I go ahead and I start. I plug in cosine squared minus 5 times cosine. That gets multiplied, that entire expression gets multiplied by the derivative of cosine, which is negative sine. Then I'm subtracting. Now plugging in the lower bound ln x. Ln x squared minus 5 times ln x. All of that multiplied by the derivative of ln x, which is 1 over x. And that is it. So like we've said all year long, these would be either multiple choice questions, or if they happen to be on free response, I wouldn't bother simplifying them. If you happen to be on the multiple choice, just maybe make note to yourself. Obviously, they might clean that up with a plus sign in the middle. And same thing here, where they could put, take out the minus and distribute and make that a plus sign next to the 5 ln x, okay? But there is no need to simplify when you are handing things in for any of your calc teachers and or on free response of AP exam. So right here, I have the formulas for basically what we just did written out. They are much more confusing to look at from the beginning to do in reverse. So the purpose of putting them after we've done the problems is so that you have the theoretical formula for it. But just to recap, all right, if you're taking your derivative of your antiderivative, that's what this notation means. The derivative of the antiderivative. Derivative of the antiderivative. You're merely plugging in when you have a constant and an upper bound of x, you just plug in x. So f of t would become f of x. That was our very first four examples. Then we have the situation where we're taking the derivative of the antiderivative from a constant to a function that is not just x. Function that is not just x. F of t dt. Okay, you're still plugging in the function f of b of x, but you have to take the derivative of the function multiplied by the derivative of the function. Then we have derivative of antiderivative of two bounds that are functions. First one, upper bound gets plugged in times upper bound derivative. Subtract, plugging in lower bound, taking lower bound's derivative. Okay. All right, that's it for this one. We'll practice in class, and if you have any questions, be sure to ask your calculus teacher. Have a great day, everybody.